This conversation is powered by Google Illuminate. Check out illuminate.google.com for more.
Welcome to this discussion on the application of AI agents in ground-based gamma-ray astronomy. The paper will be examining details the development of AI agents based on instruction fine-tuned large language models, LLMs, to address the increasing complexity of next-generation gamma-ray telescopes. What are the primary challenges that these next-generation instruments present, and how do these AI agents aim to mitigate them? The primary challenge stems from the substantial increase in complexity. Next-generation instruments, like the Cherenkov Telescope Array Observatory, CTAO, featured dozens of telescopes, leading to significantly more complex system operations and offline data analysis. Traditional methods, reliant on extensive personnel training and sophisticated software, become strained as complexity grows. The AI agents aim to automate complex tasks and provide intelligent assistance, thereby improving efficiency and user support in this multifaceted environment.
The paper mentions two prototypes integrated with CTAO pipelines. Can you elaborate on their functionalities and the specific problems they address within the CTAO framework?
The first prototype automates data model implementation and maintenance for the Configuration Database, CDB, of the Array Control and Data Acquisition, ACCADA, system. This addresses the challenge of managing the complex configuration data for the array. The second prototype is an open-access code generation application for data analysis using the Gamma-C framework. This tackles the difficulty of writing efficient and correct code for analyzing the large and complex datasets produced by CTAO.
The paper highlights the use of instruction fault-tuned LLMs. What are the key advantages of using this approach compared to traditional methods for automating these tasks?
Instruction fine-tuned LLMs offer several advantages. They can process and retain vast amounts of information, understand the environmental context, e.g., the CTAO system's documentation and code races, operate with external APIs, and communicate with humans in natural language. This allows for a more intuitive and flexible interaction compared to traditional, often rigid, automation methods. They can also learn from experience through validation against real or synthetic data.
The success of the agents relies heavily on validation. Can you describe the validation pipeline implemented in these prototypes?
The validation pipeline involves a feedback loop. The LLM generates code or data models. These are then executed within a framework containing sample data. The results are evaluated, and if necessary, the LLM iterates, generating improved code or models until satisfactory results are achieved. This iterative process ensures the quality and correctness of the output.
The paper mentions the use of different LLMs, including GPT-4o, O1 Preview, and Llama 3.3 70B. What were the considerations in choosing these specific models, and what were the relative strengths and weaknesses observed?
The choice of models reflects a balance between performance and accessibility. GPT-4o, known for its strong performance, was fine-tuned for the Gamma-P-based agent. O1 Preview and Llama 3.3 70B were also included to explore the performance of different models and to potentially offer more open-source alternatives in the future. The relative strengths and weaknesses varied depending on the specific task, with GPT-4o generally showing superior performance but at a higher computational cost.
The paper acknowledges the importance of human expertise, particularly in the absence of sufficient training data. How crucial is human involvement in the development and deployment of these AI agents, and what are the ongoing challenges?
Human expertise remains crucial, especially in the initial design, verification, and fine-tuning phases. The lack of extensive, high-quality training data specific to gamma-ray astronomy necessitates significant human oversight. Ongoing challenges include ensuring reproducibility and interpretability of the agent's actions, which are addressed by transitioning towards open-source LLMs. Addressing potential biases in the training data and ensuring the robustness of the agents in handling unexpected situations are also important ongoing considerations.
The paper focuses on CTAO. How easily adaptable are these AI agents to other ground-based gamma-ray observatories or even other astronomical domains?
The adaptability depends on the degree of similarity between the target observatory's data pipelines and software frameworks to those of CTAO. The Gamma-P-based agent, for example, is more readily adaptable to other observatories using Gamma-P for data analysis. However, significant modifications might be needed for observatories with substantially different software stacks or data formats. Adapting the agents to other astronomical domains would require retraining and potentially significant modifications to the underlying LLMs and validation pipelines.
What are the potential future developments and improvements for these AI agents? What are the next steps in this research?
Future developments include expanding the functionalities of the agents, improving their robustness and reliability, and exploring the use of more advanced LLMs and techniques. The transition to open source LLMs is a key priority to enhance reproducibility and transparency. Further research will focus on improving the user interface, incorporating more sophisticated validation methods, and exploring the integration of these agents with other aspects of telescope operations and data analysis. Investigating the potential for these agents to assist in the design and optimization of future gamma ray telescopes is also a promising avenue for future work.
The paper mentions the use of chain of thought techniques and reasoning. Can you elaborate on how these techniques enhance the capabilities of the LLMs in this context?
Chain of thought prompting encourages the LLM to break down complex problems into smaller, more manageable steps, improving their reasoning capabilities and reducing the likelihood of errors. This is particularly beneficial in the context of code generation and data model implementation, where a step-by-step approach can lead to more accurate and reliable results. The incorporation of reasoning capabilities allows the LLM to make more informed decisions based on the available information and context.
The paper highlights the use of retrieval augmented generation, or RAGI, with embeddings based on gamma-p code snippets. How does this approach improve the accuracy and relevance of the code generated by the agent?
RAG significantly enhances the accuracy and relevance of the generated code by providing the LLM with direct access to relevant information from the gamma-p codebase, documentation, and tutorials. The use of embeddings allows the LLM to efficiently retrieve and process the most pertinent information, reducing the reliance on its internal knowledge base, which may contain outdated or conflicting information due to the active development of gamma-p. This targeted access to relevant information leads to more accurate and contextually appropriate code generation.
The paper mentions the use of both real and synthetic data for validation. What are the advantages and disadvantages of using each type of data in the validation process?
Real data provides a realistic test of the agent's capabilities, reflecting the complexities and nuances of actual observational data. However, real data can be limited in quantity and may not cover all possible scenarios. Synthetic data, on the other hand, can be generated in large quantities and can be designed to cover a wider range of scenarios, including edge cases and unusual situations. However, synthetic data may not perfectly reflect the characteristics of real data, potentially leading to overfitting or inaccurate validation results. A combination of both real and synthetic data is often the most effective approach, leveraging the strengths of each.
The paper briefly touches upon the potential for future work on prompt optimization. How could optimizing user prompts further enhance the performance of the AI agents?
Optimizing user prompts can significantly improve the performance of the AI agents by ensuring that the prompts are clear, concise, and unambiguous. While structured prompts can guide the LLM towards generating more accurate and relevant code or data models. Techniques like few-shot learning, where examples of successful prompts and their corresponding outputs are provided, can further enhance the performance. A supplemental agent dedicated to prompt optimization could analyze user prompts, identify potential ambiguities or inconsistencies, and suggest improvements, leading to more efficient and effective interactions with the AI agents.
Finally, what are the broader implications of this research for the future of ground-based gamma-ray astronomy and other fields of astronomy?
This research has significant implications for the future of ground-based gamma-ray astronomy by enabling more efficient and effective use of complex instruments like CTAO. The automation of tasks and the provision of intelligent assistance can significantly reduce the workload on researchers and engineers, allowing them to focus on scientific analysis and discovery. The techniques and methodologies developed in this research are also applicable to other fields of astronomy, potentially revolutionizing data analysis and instrument control across the astronomical community. The development of AI agents for scientific data analysis has the potential to accelerate scientific discovery across various domains.
The paper mentions the use of Pydantic classes for data modeling. Can you elaborate on the advantages of using Pydantic in this context?
Pydantic is a Python library that provides data validation and parsing capabilities. Its use in this context offers several advantages. First, it allows for the creation of strongly typed data models, ensuring data integrity and consistency. Second, it simplifies the process of validating data against predefined schemas, reducing the risk of errors. Third, it integrates well with other Python libraries and frameworks, making it easy to incorporate into existing data pipelines. The use of Pydantic contributes to the robustness and reliability of the data model implementation and maintenance process.
The paper mentions the use of LaTeX for providing context to the LLM. Why was LaTeX chosen as the input format, and what are the advantages and disadvantages of using LaTeX in this context?
LaTeX was likely chosen due to its ability to represent structured information clearly and unambiguously. The structured nature of LaTeX facilitates the extraction of relevant information by the LLM. Advantages include the clear separation of content and formatting, which can aid in the parsing process. Disadvantages include the potential for increased complexity in processing latex compared to simpler formats like JSON or plain text. The choice of latex reflects a trade-off between the clarity and structure it provides and the potential processing overhead.
The paper mentions the use of HESS DL3 public test data for validation. Why was this specific dataset chosen, and what are its characteristics that make it suitable for this purpose?
The HESS DL3 public test data release was likely chosen due to its relatively small size, which allows for relatively quick validation. This is important in the iterative development process where rapid feedback is crucial. The dataset's characteristics, including its format and content, are also likely compatible with the GAMMAP framework, making it a convenient choice for testing the code generation capabilities of the agent. The availability of public data is also a key factor, ensuring reproducibility and transparency.
The paper discusses the challenges posed by multiple incompatible versions of GAMMAP in various LLM training sets. How did researchers address this issue in the development of Astro agents?
The researchers addressed the issue of incompatible GAMMAP versions by employing retrieval augmented generation and using embeddings based on specific code snippets from the relevant GAMMAP version. This approach allows the agent to access and utilize the most up-to-date and relevant information, reducing the risk of generating code based on outdated or incompatible versions. The use of RIA ensures that the generated code is consistent with the specific GAMMAP version being used for analysis.
The paper mentions the potential for a supplemental agent to optimize user prompts. Can you envision other potential applications of AI agents in the context of ground-based gamma-ray astronomy beyond those discussed in the paper?
Yes, there are many other potential applications. AI agents could assist in real-time monitoring of telescope operations, automatically identifying and responding to anomalies. They could also be used to optimize telescope scheduling and pointing, maximizing observation efficiency. Furthermore, AI agents could assist in the development of new data analysis techniques, automating the exploration of different algorithms and parameter settings. They could also be used to generate scientific reports and publications, summarizing the results of observations and analogies. The possibilities are vast and continue to expand as AI technology advances.
The paper concludes by mentioning the importance of transitioning to open source LLMs. What are the key benefits of using open source LLMs in this context?
The key benefits of using open source LLMs include increased transparency, reproducibility, and community involvement. Open source models allow for greater scrutiny of the model's training data and architecture, reducing the risk of biases and ensuring the reliability of the results. The open nature of these models also facilitates collaboration and community contributions, accelerating the development and improvement of the AI agents. The use of open source LLMs promotes a more inclusive and collaborative approach to scientific research.
This has been a very informative discussion on the exciting applications of AI agents in ground-based gamma-ray astronomy. Thank you.